Section 6.8 is about the shape and polarity of molecules, so we can actually use Lewis structures in order to predict the three-dimensional shape of molecules, and we can do this by actually counting the number of electron groups and bonded atoms that are around the central atom. We can also predict the polarity by looking at the number of lone pairs around the central atom. So, valence shell electron pair repulsion theory actually tells us that electron groups are arranged as far apart as they possibly can get around the central atom. Because remember, electrons have negative charges, so they're going to repel each other. So in order to minimize the repulsion, they're going to stay as far apart as they can. So there's actually two different types of geometry. There is electron geometry, where you count the number of electron groups around the central atom. Electron groups are lone pairs, single, double, and triple bonds. They all count as one electron group. There is also molecular geometry, where you count just the number of bonded atoms that are around the central atom. Your book calls this the shape of the molecule. They don't call it molecular geometry, but this is the term that I'm used to, so that's the one that I'm going to use. But if you look in your textbook where it talks about shape, that is the same as molecular geometry. So it's just the number of bonded atoms around the central atom. So it's really just looking at both. So, for example, I'm going to draw our CO2 that we drew earlier with our 4 lone pairs around each oxygen and 2 double bonds between the oxygen and the carbon. So, in this example, we have 1, 2 electron groups. We have 2 electron groups, and we have 0 lone pairs on the central atom. So 2 electron groups, which is also 2 bonded atoms. So our electron geometry is linear. Our molecular geometry or shape is also linear. Okay, so there's a table that you can follow in your textbook, table 6.16, to figure out what the electron and molecular geometry are. I'm going to write out a table in your notes here before we do another example. So this is not the same table from your textbook, but it's pretty much the same. So we're going to have a column that tells you number of electron groups, number of bonded atoms, the electron geometry, or the electron group geometry. That's what your book calls it. And then the molecular geometry. Alright, so if the number of electron groups is 2, the number of bonded atoms is 2, then it's going to have a linear electron geometry and a linear molecular geometry. So that's like the CO2 example we just did. If it has 3 electron groups and 2 bonded atoms, then it's called trigonal planar. And if it only has 2 bonded atoms, the molecular geometry is called 120 degrees bent. If you have 3 electron groups and 3 bonded atoms, then the electron geometry is trigonal planar, and so is the molecular geometry. Alright, so now if you have 4 electron groups and only 2 bonded atoms, then it's tetrahedral. And 109.5 degrees bent. If you have 4 electron groups and 3 bonded atoms, then it's tetrahedral electron geometry, and it's called trigonal pyramidal molecular geometry. That should be an A, not an I. P-Y-R-A, pyramidal. Okay, if it has 4 electron groups and 4 bonded atoms, then the electron and the molecular geometry are both tetrahedral. Alright, so we'll look at a few examples of all of these different types of geometries. So we had our linear electron and molecular geometry. So now let's look at groups that have 3. Alright, so here's one example. So this example has 3 electron groups and 3 bonded atoms. So if we scroll back up, 3 electron groups and 3 bonded atoms, it has a trigonal planar electron geometry, and a trigonal planar molecular geometry. Okay, our next example, if we have this molecule, so this is going to be SO2, and here is the Lewis structure for SO2. Okay, so in this case we have 1, 2, 3 electron groups, but we only have 2 bonded atoms because we have 1 lone pair. Okay, so the electron geometry, I'm just going to start making a table. Okay, so the electron geometry here is going to be trigonal planar, So we have 3 electron groups and only 2 bonded atoms. So electron geometry, trigonal planar, molecular geometry, 120 degrees bent. So the actual molecule for this looks a little like this. So this is kind of a crude sketch of it, but it's going to have a 120 degree angle here between the 2 oxygens. Alright, if we have something like this, so we drew this earlier, CH4, there is your Lewis structure. So we have 4 electron groups and 4 bonded atoms. So our electron geometry is tetrahedral, and our molecular geometry is also tetrahedral. Next example, NH4, or NH3, I'm sorry. There's only 3 hydrogens, not 4. There is our Lewis structure. So we have 4 electron groups, because remember, lone pairs also count as electron groups, and we only have 3 bonded atoms. So the bonded atoms are the ones that have the lines between the 2, or between the central atom. So our electron geometry is still tetrahedral. So we have 4 electron groups, but our molecular geometry is trigonal here in the middle. Next example, just to show you what these look like again, we have H2O, or water. We have 4 electron groups still. We have 2 lone pairs and 2 bonded atoms. So we have only 2 bonded atoms. So again, our electron geometry isn't going to change. It's going to be tetrahedral because we still have our 4 groups. But our molecular geometry is going to be different. It's going to be 109.5 degrees bent. So water looks something like this. This filled in circle represents our oxygen, and then these molecules here represent our hydrogens. So there is an angle of 109.5 degrees between the 2 oxygen atoms. Alright, so now we have an example for all of our different groups of electron and molecular geometry, depending on the number of electron groups and the number of bonded atoms. So now let's talk about how you use the shape to predict polarity. So if the molecule has a lone pair, it is considered polar. Because remember, polar means that it's an unequal sharing of electrons. So because of that, these electrons are not being shared equally between all of the atoms. So since this has a lone pair, it's polar. Water has 2 lone pairs, it's also polar. CH4, there are no lone pairs on the central atom, so it's nonpolar. Another way you can tell is all of the groups are the same around the central atom. So if all the groups are the same and there's no lone pair, then it's nonpolar. If we go back to our other examples, SO2 is polar, it has a lone pair. And this molecule, it has 2 different atoms bonded around it. So even though it doesn't have a lone pair on our carbon, there are two different types of atoms connected to it. So this is also considered polar. So if it has more than one type of atom or different atoms around it. So different types of atoms. So it's also considered polar. If we go back to this example, we have two groups that are the same and there are no lone pairs of electrons on our central atom. So CO2 is nonpolar. Alright, so for molecular geometry and electron geometry, you need to draw the Lewis structure and then look at the number of electron groups and the number of bonded atoms. And remember, electron groups are lone pairs, single, double, and triple bonds. They all count as one electron group. Molecular geometry, you count the number of bonded atoms. And when you draw a Lewis structure, if it has a lone pair on the central atom, it is polar. If it has different types of atoms around the central atom, it's also polar. If there are no lone pairs around the central atom and all of the atoms are the same around it, then it is non-polar.